Hello and welcome to CEM and Lucidity Systems Wednesday webinars on separation solutions. Today's presentation, Making Gas Chromatography Greener Using Common Sense Optimizations, Simplified Methods, and Miniaturized Instrumentation, is presented by Dr. Nicholas Snow of Seton Hall University. Before we get started, let's review some of the features of GoToWebinar. The audio for this presentation is available on your computer only. If you cannot hear audio, please check your speaker volume. To access the handouts for this presentation, click on the handouts icon and then click the handout you want to access. The handout file will automatically start downloading from your default web browser. At the end of the presentation, we will have a question and answer session. You are welcome to submit questions at any time during the presentation. To do this, please type it in the questions section and click send to submit your question. Please note that not all questions may be answered live, but they will be answered by email after the webinar concludes. It is now my pleasure to introduce today's presenter. Dr. Nicholas Snow is Professor of Chemistry and Biochemistry and Director of the Center for Academic Industry Partnership at Seton Hall University. He is currently teaching advanced undergraduate and graduate courses in analytical chemistry and separation science. He has been recognized twice by the Seton Hall University Board of Regents for outstanding teaching and service to students. He maintains an active research group with projects involving rapid separations of complex mixtures, multidimensional separations, sampling techniques for chromatography, gas chromatography, and gas chromatography mass spectrometry. He is especially interested in working with industrial and private partners in solving difficult analytical problems. With that, we are ready to begin our presentation. Nick, over to you.
Good afternoon. I'm Nick Snow, and I'm coming to you from rainy South Orange, New Jersey, and very glad to be here speaking in the Lucidia and CEM series of webinars. Today I'd like to talk a little bit about making gas chromatography greener using some common sense optimizations, some simplified methods, and some miniaturized instrumentation. I'm Nick Snow here at Seton Hall. I'm going to be presenting to you today. The rest of the names on here, James Mavesky, Genevieve Cox, Ria Sandeep, Cassandra Maratri, and Bitha Beji, are my gang of students. James is a graduate student, and Genevieve, Ria, Cassie, and Bitha are all undergraduates, and they really do the hands-on stuff in the lab, and they're really the folks that are doing a lot of the data. Plus, some of the data we're going to see today was actually done by some of my former students. So we're going to think today a little bit about what we can do to use gas chromatography greener, and also think about how we might do that using some of the very interesting technologies that we see from CEM and Lucidity. So let's think a little bit first about the principles of green chemistry. What is this all about? What's this whole idea of green chemistry? And I think the American Chemical Society tells us a little bit about that. They've got a very nice website on the whole thing. And we're going to think a little bit about the principles of green chemistry and how perhaps do they apply to analytical methods. First of all, we think about preventing waste. Analytical methods use a lot of waste. A little later on, I'm going to talk about solid phase microextraction. And of course, you can almost think about that as really the beginning of green analytical chemistry. But we think about using solvents. We think about using power. We think about time efficiency. What about designing for energy efficiency? I think that's one thing we're kind of interested in about Lucidity's mini GC is that it is a smaller box. It uses less energy than a full-size instrument, and I think that can be very attractive. But we think about our whole process. What about reducing amounts of reagents and derivatives that we use? And we're always, of course, thinking about safety and accident prevention. How do we keep everything safe? So here's a little bit of an analysis of that, a little bit of a modern analysis. Again, I apologize. I think my little image may be across the blue oval here. Blue is productivity, but here is RGB green chemistry analysis from Analytical Chemistry, about 2019. I'll mention these guys again a little bit later, but it's kind of interesting to think about how you might think about an analytical method in terms of greening it. And what they do is sort of use a color scheme where red is analytical performance. If blue is productivity and practicality, And then green is safety and eco-friendliness. So there's your greenness. Now match up the colors. We've seen triangles before. It kind of looks like one of those triangles we may have seen in method development before. But it's kind of interesting to think about that those are really all factors that we're going to think about now in developing analytical methods. We're not just going to think about analytical performance and productivity. That's pretty much all we thought about until we started thinking about green chemistry. Now let's think about greenness as well, and where does that fit? And it's kind of interesting to think about this, and here's a question I'll throw out to you that I'm not sure has an answer yet. Does yellow, which is the combo of red and green, is yellow actually the enemy of blue? If you've got great analytical performance and wonderful eco-friendliness, does that make the method impractical? Likewise, is red and blue or magenta the enemy of green? So many of our methods, especially legacy methods, have great analytical performance. They're wonderfully productive, but how green are they? That's a great question. And then finally, are green and blue together highly productive and highly safe? Is that going to sacrifice performance? Where is cyan the enemy of red? And I think that's an interesting question. It's not one that we've answered fully yet, but it's one that we can start thinking about. Can we think about these three factors? Do they work together or do they work against each other? Novak and Kostelnik, I think pretty much think they'd like to work together with them, and that's where they come up with combining them to make a method that's white. I'm not 100% sure of this. It's something I'm thinking about a lot, and it's something we should all be thinking about a lot as we consider analytical methods. Let's think about gas chromatography now and make some assumptions. And I show a picture of an old green book that some of you, if you've been around for a while, may be familiar with. It's the original edition of Basic Gas Chromatography by McNair and Benelli, probably the book for gas chromatography in the first 50 years of GC or so, published originally in 1965, where we learned a lot of GC in that. But I love the green cover, and I think one of the green assumptions we make to start with is that GC is not green. What do? We heat things in ovens and stuff like that. How green can that be? Sample prep. Most of our techniques are not green. That's an assumption we make. One thing we do in gas chromatography all the time is inject 1 microliter of liquid. That's what we do. Question, how much solvent do we really need? Miniature systems and extractions can be good, and I think we'll see some of that technology a little bit later. And another assumption that we make is that we tend to see a lot of chromatograms, especially in vendor application notes and places like that, where they have a lot of baseline. Looks good, but hey, if I'm generating if all I'm looking at is baseline, am I looking at data that I'm using? No. So think about that in terms of efficiency. All that baseline looks good. Your peaks are lovely separated, but boy, you could be doing something much more useful with that time, couldn't you? And much more efficient. So those are some of the assumptions that we see in so many GC gas chromatography methods today. Let's take a look at sample prep. And this is, I'm going to borrow from Ron Majors and Doug Rainey. LCGC magazine typically every several years does a sample prep survey. And this is Ron's data from 2013. You probably can barely see it, but trust me when I tell you, if I can pull my arrow in front. Can I pull my arrow? It doesn't want to look at my arrow. That's okay. But if you look down at the bottom of this, you're going to see techniques like weighing, filtering, centrifuging, dilution, evaporation, sort of really basic laboratory techniques are what we all do. To come up to a CEM technique, you have to go almost all the way to the top of this before you get to microwave assisted extraction, which is at about number 10%. It's all the way, it's the fourth one down from the fifth one down from the bottom or from the top on this chart. So that's one of the interesting things, is that we see a lot of our sexier techniques like MAE, SPME. One thing interesting you don't see on this chart at all in 2013 is catchers, which is very popular and is really being touted as somewhat of a green technique. We don't see that at all, but that's one thing we see. We see a lot of our standard techniques. You can get the reference for this. I'm pretty sure they're going to make these slides available to you on demand or something. If they do, you can get the reference for this, but check out LCGC sample preparation perspectives column, and you can get this information. This was 2013. Here's 2016 that Doug Rainey did. It's the most recent data, at least that I became aware of. And you can see pretty similar. Dilution, weighing, filtering, centrifuging, adjusting pHs, liquid-liquid extraction, very, very popular techniques. A lot of these, what I see here is a lot of potential to get greener. You can see microwave is still up there near the top, but it seems to be getting a little better. It's not the 5th from the top, it's more like the 10th from the top now, which is getting better. And actually you now do see catchers and some of these other techniques in there. So that's one of the things also to think about. How do we, here are the techniques that we use for preparing samples. How do we switch to a new technique that might be greener than our old technique? But think about that idea. Is it greener? Is that going to cost me practicality? Is that going to cost me in detection limits? What's it going to cost me to do that? Hopefully I can do that at minimal cost to my other interests. Here's some other information in Doug's article talking about techniques, and he gives some detail on that. And you can see at the bottom on the left here, you can see the technique slide talks a little bit about solid phase extraction as kind of the standard, and the blue is users, and the red here is literature. For the techniques, and one of the things you can see very interestingly is that solid phase extraction, he kind of set that to 100%. Lots and lots of literature on SPME, and I'm going to share some of that with you today as well, but fewer users. Very, very interesting. And on the other hand, looking at microwave assisted extraction, not as much, but you see more users than you see literature. So what I see actually as an academic, I see that as an opening. I see that as an opportunity first to engage with users and find out what your real problems are, but then to think as an academic about how we can make it better. And I think that's very exciting about MAE, let's say in combination with GC, and some of these other techniques. SFE has still got some footing out there. I've used it to analyze fat in candy bars and things like that. So a lot of fun. But you see actually when you look at where the blues are, MAE, catchers, purge and trap, solid phase dispersion, kind of right there, sort of behind classical, and now SPME is a classical technique, classical extraction techniques. Interestingly enough, Doug didn't put liquid-liquid extraction on here. I would put that probably somewhere right around solid phase extraction as well. So we do have the opportunity to do things like take methods like SPE, liquid-liquid extraction, and green them up with techniques like SPME or microwave-assisted extraction. So very interesting opportunities there. Taking a look at some of the analytes, and this is another reason why it's very interesting to think about our sample preparation techniques. Analytes are really getting all over the place. When you think about that and think about what Doug's survey says here, they are really all over the place. You could be anything these days, and you could run into anything these days. Pharmaceuticals are still kind of driving the boat, but a lot of these things are catching up here, and even the pharmaceutical folks are getting interested in some of these other types of compounds because they're using them, and the FDA is getting very interested in the fact that they're using them. So we have all kinds of, we have a massive group of, a large group of techniques, we have a large group of analytes at our disposal. So how do we think about all of this then in combination with gas chromatography? Well, let's think a little bit about extraction a little bit more. And one thing we always think about with extractions is selectivity. So this is a theory slide that I used in Modern Practice of GC many years ago in that book. And when you think about extractions, you see the blue line at the bottom is a very low partition coefficient. The lines at the top represent high partition coefficients. And what that tells you, not surprisingly, is if you have a high partition coefficient, you can extract a lot quicker and easier. So that usually says go to a high partition coefficient, but it also leads to some thinking that, I can still extract even if the partition coefficient is low. That helps me think about solvent choices. That helps me think about extraction mechanisms. It helps me think about, and we may see some of this data, maybe a type of extraction where, I might extract in a microwave assisted system into water instead of extracting into an organic solvent. And water, of course, is a much greener place to go than that organic solvent. So those are the kinds of things that we might think about and come back to our partition coefficient. How do I handle the fact that I don't extract as much? Maybe I'll use a more sensitive detector or a larger volume injection or something like that with my gas chromatograph. But we can really get in there and think about the chemistry to help us green our methods, to help them be more efficient. At the end of the day, for those of you in business and industry, to help you save money. And you can get green. I think you can be green, be efficient, and save money all at the same time when we're thinking about sample prep and when we're thinking about GC. Let's think about some other assumptions. We inject 1 microliter of liquid all the time in gas chromatography. Well, we can do some other things with that. I like SPME. I was one of SPME's first adopters 30 years ago now. I did my first SPME injection. It was before SPME was even on the market. I did my first. And also one thing that's been a little bit overlooked in gas chromatography is just injecting larger volumes. And inlets today for GCs that come on a lot of the larger, laboratory systems can do that, can inject larger volumes. One thing you might want to think about, you can buy a little bit more sensitivity. As long as you're conscious of how much solvent you're injecting, just try injecting a little more. If you're doing 1 microliter, try 2. See what happens. Here's some of the early milestones in SPME because it really starts off thinking about green analytical chemistry. It actually goes way back to 1987, and Pavlician at the University of Waterloo is really and his students. Catherine Arthur really was the student who was lucky enough to get the first paper in 1990. But that was kind of interesting. And actually, when you think about it, the history, and one thing to think about too. SPME the term was coined in 1990, but the actual process goes back further. Several years before that they were working on it. But here's a trace analysis, and one reason we like things like SPME for saving solvents, this was actually done in my lab about 25 years ago now by a high school student. FID system. We could do this. In fact, maybe I'll speak with. I'll try to have my students. Maybe we could probably repeat this one very nicely on the mini GC in our lab now, and probably do something fairly nicely with that. This was done 25 years ago on a 5890 gas chromatograph, BTEX. At 400 parts per trillion. One thing you find out, there's lots more peaks here than 4. Everything is contaminated at 400 parts per trillion, and that's something that we deal with. So think about that, and we'll think about that. We'll think about that. So other things we do, and we talked about it a little bit, if we're into reactions, if you're working pharmaceutical or clinical land, you do things with derivatizing. We were the first lab to actually do a derivatizing reaction on an SPME fiber. We did that also about 25 years ago. My student Pius Okeo and I drew these figures, these very simple figures. And what we did was we just did the extraction, followed it up with a derivatizing reaction, which was kind of interesting. We could run a whole batch of samples with about 20 microliters of derivatizing reagent instead of putting derivatizing reagent in every vial, a lot less nasty reagent that we used. We could do a whole batch of samples and then inject. And this was one of our first chromatograms back then. Pius and Steve and I did this one, and there is our trimethylsilyl 17-beta estradiol. And of course, that's also kind of a long literature now of SPME of drugs. And when I think about early green applications, SPME really greened up gas chromatography analysis, and that was a large part of the point. So here's a little bit later on, just some steroids that Pius and I did some years ago. But you think about this compared to, if any of you are out there doing solid phase extraction of steroids, you know how much fun that is. And we got SPME to work with this fairly well, and certainly greened it up. Now we can automate it. Back then, the automation was Pius, was the graduate student. He did all the injections manually. Now, of course, automated SPME, and we were a part of bringing automated SPME and automated SPME derivatizing onto those nice rail auto samplers that you see everywhere. The first macro for the rail auto sampler was actually written by a person from from the manufacturer in our lab to help us in our lab. They wrote the macro for it in our lab, and I was too kind. I just let them take it back with them. But now that's on. That capability exists on all of those auto samplers now. So from this, here's a little bit later work where we're again kind of greening things up, looking at a steroid mixture now at 1 ppb, 1 nanogram per milliliter. And it was actually kind of tough to contrive this chromatogram to get the peaks to overlap, but we did that on purpose to show another benefit. And one thing we can do if we want to build sensitivity and selectivity into a method, maybe we make the method less selective so we don't have to use so many solvents, but then we use a technique like GC times GC to pull apart from that. And that's another one of the things that we can do. You saw that last chromatogram had a few peaks. Here's the same dozen or so drugs by GC times GC, and we see that they're all separated. And I think that's also a pretty exciting way that we can go. But of course, GC times GC is a bit of a power hog, and certainly GC times GC TOF is also a power hog. So we're trading some green. This is an example, actually, potentially of trading greenness for selectivity. And that's one of the things that we're going to think about quite a bit as we bring analytical methods into green chemistry. Now, one challenge that we have is it's not just a reaction that we're doing, but we do sample preparation, instrumental analysis, and then we're doing it over and over and over again. And we need to think about that as we think about trying to green it up and as we think about the assumptions that we make while we're doing that. So here's the same thing actually done on a different system, on a triple quad, the same similar steroid mixture. These peaks here in the middle, you see the three peaks in the middle, the estrone, the estradiol, and those would be overlapped pretty much chromatographically. Probably 4 out of these peaks would be overlapped chromatographically, but we pull them apart with the detector, and that's another place where we get selectivity. It's also another place where we get very low detection limits. But again, a triple quad is kind of a power hog. So it's another one of those things. When I go back to that early slide with the RGB idea on it, if I'm going to the triple quad, yeah, one thing I'm going to want to do, and we loved SPME for this, I'm making up for that maybe by not using so many solvents. So I'm getting kind of green because I'm still using I still need an instrument that's a power hog to get down to parts per trillion. But at the same time, I can green it up by doing SPME, and this is with everything pretty massively optimized. And you can see here, actually, the reference here, Scientia Chromatographica, is a fully open access journal, so you can download that paper freely. One thing I'll just mention briefly is large volume injections. We can do a PTV, a multimode. Why not? Yeah, you can increase your sensitivity just by injecting more, and that's again something that tends to come on the larger systems, laboratory full-size systems, but it's something to think about. One thing I know that CEM and Lucidi are talking a lot about these days are carrier gases. I've become a fan of nitrogen, and I think a lot of folks, are working with wanting to work with hydrogen. And we remember, of course, this is the plot that everybody posts and shows you online about why should you do this. And you see helium's kind of in the middle here. Nitrogen, everybody says don't use nitrogen. Everybody says you must use hydrogen. That's a question that I'm actually working on. I'm very interested in this question. And I've done actually had a student, Brittany Hanzo, whose work I'll show you in a moment, did her master's degree thesis running nitrogen. And we've been running nitrogen in our mini GC until they sent us the mini gas, so we're now running hydrogen. And we've got, and it's kind of interesting that you can actually get the lowest HETP with nitrogen, but you have to optimize carefully, a low flow rate, and you get a pretty steep mass transfer. Here's a problem with all of this, and everybody puts this slide up. You'll see it, and everybody who's talking about using hydrogen puts this picture up. It's isothermal. Do you do isothermal GC today? Probably not. This was done back in the 1980s. Are we using the same technology in the 1980s for running our pneumatics and all of that stuff today? No. This was probably done even using manual injection, and who knows about the pneumatics. So it's time to actually update that thinking. I did write an article in LCGC magazine. This is actually Brittany's work. And one of the things you see in Brittany's work here is that, the peaks pretty much look the same. You will see a retention time shift if you change carrier gases. Again, EAS 2019, my lovely videos covering that up, and Brittany's master's thesis that you can download from Seton Hall. And it's a free download. You might want to look at that if you're considering nitrogen or considering carrier gases. Take a look at Brittany's master's thesis. It's a free download. But we found pretty similar performances, and also in temperature programming. Again, same thing, nitrogen, helium, hydrogen. One thing you're probably not going to sacrifice is performance. Hydrogen probably won't perform as well as advertised, because that Van Deemter plot was isothermal, and Giddings back in the 1960s wrote a very nice paper in the Journal of Chemical Education, 1962, volume 39, talking about temperature program GC. Also, my article in LCGC about 2019 talks about how temperature programming really works as kind of a step function. So the carrier gas choice has it does have an impact, but it's a lower impact in temperature programming, I would say, than in isothermal separations. So one thing you'll have to do some optimizing of your method if you change carrier gas from helium to nitrogen or hydrogen. And I recommend giving it a shot. Talk to CEM and Lucidi about the mini gas and see what you think of that, and give it a shot, or hook up your gas generator and run carrier with it. You'll probably be pleasantly surprised. The gas generator vendors want you to buy a more expensive gas generator to do carrier, but you may not need to. Give it a try, see what happens. You probably don't need to. And Giddings theory tells us a little bit why in temperature programming, you'll have to do some optimizing. The retention times will shift. You may see some resolution changes, but that's okay. You won't have to do as much optimizing as you think from those isothermal plots. You'll probably be pretty close just by put in your same conditions and run it the first time and do a little bit of optimizing after that. So a little bit of discussion there. I think they're both potential alternatives, good alternatives to helium today with capillary columns and temperature programming. Just make sure your lab, of course, with hydrogen, make sure you're set up with ventilation, make sure your safety people don't barf on you for that sort of thing. Just be a little careful there. Be very careful with leaks. With hydrogen, of course, make sure you've got a good electronic leak detector and check often if you're using hydrogen. Most of our theory is really based on isothermal GC, what you read about in the books, what you see in basic GC. That Van Deemter plot, those Golay plots are all done isothermal. So think about it is, again, we do temperature programming. So I think you're going to have to do less optimizing than you think if you make the switch. Nitrogen is wonderful because it's low cost. You can buy tanks of it for almost nothing. Get a great big liquid nitrogen doer and suck the gas off of it. It might last you for years. Hydrogen, on the other hand, we do need a generator. It's going to be a capital expense, but those are becoming less expensive and smaller. That's one of the reasons that we're all here today with CEM and Lucidity. More work on different columns. Yeah, that's one of the things. I think that's one of the things that will come out there. Maybe, you just never know if some strange thing is going to happen if you switch to hydrogen on one of the more unique stationary phases. Do keep an eye out with your detector compatibility. If I run nitrogen, my old GCMS really was not happy with that. In fact, it just overloaded the ion source big time. I saw a lot of noise and no peaks. Newer GCMSs may be able to tune that out, but it's something as you will get nitrogen signal that you'll have to deal with. But hydrogen, on the other hand, works quite well. Okay, here we go. Let's take a look at some chromatograms. And oops, I confused it. I got a dingy noise here, but here's some chromatograms on the Mini GC, some lavender oil that Bitha, my student, is running, and you can see here it looks like lavender oil. It looks like some of the biggest components. There's linalool and linyl acetate. If you look at essential oil separations, we're looking at the Mini GC from Lucidity. I love the thing. I'll show you a picture of it in my lab in a moment. Small box, simple instrument. Yeah, we're getting performance that sure looks like the benchtop GCs that have the bigger benchtop GCs that I've worked with before. So we're pretty happy with that. Here's another one. Here's one. So Bitha is doing some extracts of valerian root, which also is one of the places where lavender oil comes from. And again, we see some pretty nice data there that shows us this is what an extract in microwave-assisted extraction. I didn't put a lot of conditions here. I'm really just showing examples right now. But you can see the kinds of things that we can do with microwave-assisted extraction married up to something like a Mini GC when we're thinking about greening our instrument profile, thinking about saving some lab bench space, the microwave-assisted extraction, and the Mini GC. This was a simple extraction. I think she just went, actually she went straight into water and then diluted the thing with methanol. And got this wonderful looking chromatogram with all kinds of peaks on it for us to identify, eventually identify by GCMS and things. But yeah, this is the kind of thing that we're, that even now the miniaturized systems are doing very nicely, the kinds of things we would have done on a full-size system in the past. So here it is in my lab, and I wanted to show a few things. Actually, I thought the picture, as I took the picture, I was thinking, this is kind of interesting to look at. So if I took this picture and panned further to the left, one thing you would see is probably right next to this, within a few feet of it, is one of the most complex systems you can buy. There's a triple quad LCMS sitting to the left of that, just past those electrical boxes on the way to the left. That's actually where a triple quad LCMS is plugged in from PerkinElmer. Way back in the back where that hot nitrogen doer is, there's the GC times GC TOF system. So you can see a little bit of the compare and contrast when we think about greenness and think about what you want to do. I think in method development, spend a lot of time thinking about your method goals. And how do those method goals match up with what your instrumentation is that you're looking at? With certain things I need to do on that GC times GC TOF, but not everything. And that's something I want to think about. But you can see that has a doer, 2 gas tanks, and it's a great big system that's a power hog. You can actually see right behind the mini gas, which is in the middle of the picture here, right behind that is a traditional benchtop system from another vendor. And again, you can see that probably the mini gas and the GC itself fit in almost the same lab space, or maybe about half the bench space that the GC and a traditional hydrogen generator fit in the background. You can see that. So I'm really getting to be a fan of mini systems for greenness. I'm going to make a constructive criticism with a smile, and I'm saying this with a smile for Lucidity and CEM. The box is black, and we do talk about black boxes a bit in the educational world. Let's not turn GC into quite a black box just yet, but they are pretty good. The black box is performing quite well. And certainly, then actually I'll say one thing also with a smile, the students love the the LEDs and the colors and all of that with the GC. Students are pretty excited about that. Whole thing run off a laptop, and literally when this system came, the GC, the mini gas, everything, we were up and running in probably not much more than an hour. We pull it out of the box, put everything on the bench. flipped it on, hooked it up, and we were up and running fast, which was a really nice thing about this, putting this system in the lab. Also, you'll see in the background there, you'll see the Discover microwave assisted extraction system, all right there together. You could envision all of that being together in the space almost of one traditional benchtop system. So not bad. And actually, if you look further over to the right, there's an even tinier GC all the way in the right in the background. In front of that, there's also an old turbo pump. So some things that go on in my lab. All right, let's take a look at a few other things. One thing you probably also have never done is taken the covers off. So here's the top cover removed from the mini GC, and you can see it's a pretty complex box, a pretty small, compact box. But all the usual things are there, and all of the usual stuff that you expect. One nice thing about this system, which I do like about some of the miniaturized system folks, really are thinking about also using traditional fittings. In fact, I took the top fitting off of an old Agilent GC, and I stuck it on this one because it seemed to behave better with some of my syringe needles. So that worked out very nicely. So a couple of other things. Here's the column from the mini GC. Again, a much smaller column oven, much smaller column. That actually enables them to temperature program pretty fast. So we like that as well. But the connections on this particular one are permanent. I know they're working on some less permanent connections to make it a little more convenient to trim columns and change them and things like that. So we think about method development, and this is the classic triangle. You think about it: resolution, ease, capacity, greenness. These are all things we should be discussing as we move into method development, as we think about method development. So a few common sense optimizations. It looks like my timer here says I have about a minute and a half left. Sample prep, we really can green it up. We can do SPME, we can do sortative extractions, we can do microwave assisted extraction, we can do all kinds of techniques that CEM and Lucidity work well with to do that. One of the things I suggest to everybody: talk to your vendor. Get to whoever your vendor is. You may be working with the folks here, you may be working with other vendors, but the vendors are actually out there wanting to help you. Of course, they want to sell you things too, but they also really want to help you and help your methods be successful. I think most of the vendors in chromatography really do feel that they want to build a relationship with their customers. So take advantage of that and use it. Get them to show you things. It's pretty amazing what the vendors are doing these days across the board in this discipline. Get out there and see it. Nitrogen and hydrogen, lots of labs are switching to hydrogen. Nitrogen might be acceptable. Here's some acknowledgments. I've got a graduate fellowship, and also I hold a professorship. Thomas and Sylvia Tensa, Seton Hall, of course, Millipore, Sigma, and Shimadzu have been good to us. And the best for last, of course, Lucidia and CEM hosting this webinar, helping us out. They've been, again, one of those vendors that really loves their customers. Finally, I'm going to close with a few shameless plugs of 2 books. You'll see a pretty familiar name in this webinar on those 2 books. If you want to learn more about GC times GC, want to get the basics of GC. This is the famous McNair-Miller book. We saw the green version from 1965. And then 2 journals. Green Analytical Chemistry is brand new, Volume 1, Issue 1. With that, I'm going to say thank you very much. I'm up to 30 minutes, so we will take some questions. And thank you all very much.
Thank you, Nick. That was very interesting. We will now begin our question and answer session. As a reminder, to submit a question, please type it in the space provided and click Send to submit.
All right, then we do have a few questions. So our first question is, can SPME be done with miniaturized systems?
Oh, that's Nick here. I assume you can hear me. That's
Yes,
unmuted. That's a great question, and I think there's some nice potential to do SPME with miniaturized systems. Again, you might have to take it right now. You might have to take a step back to the way we did it years ago, which get ready to kind of use yourself as the auto sampler at first. Because you would need pretty much, if you want to do automated SPME, you'll need a rail type auto sampler or something like that. But I think there is potential there. One of the things I like about the Lucidity system is that it actually uses the same inlet liners and the same inlet geometry that you see on a traditional Agilent or old, back in my day, an old HPGC. So it's all the same inlet liners, same inlet geometry, which means SPME should work like a charm on it. And that's one of the nice things I like about what's going on with some of these miniaturized systems is that they're still using components where you interact with them, like the inlet from larger systems, and I think that's a good thing. And that actually makes it flexible, that anything you could put into that Agilent inlet, you can probably stick into the Lucidity inlet as well.
Excellent. Well, that's good to know.
Hey,
So,
Lee,
Nick,
Mhm.
yes.
sorry, this is Alicia here. I was just going to chime in a little bit on this question as well. Kind of plug next Wednesday, Dr. Emanuela Gianfrido.
Oh,
I
that's
think,
right. Yes, she's coming.
yeah,
She's an SPME a real leader there these days.
exactly. And I think she's going to show you some SPME work on the mini GC itself. So.
Terrific, terrific. Yes, so certainly give it a try. Um,
So then, what are some challenges with making a GC smaller?
I think that's actually, I really enjoyed when was very happy when Lucidity showed me how to open the cover on the box and look in there. And I think the big challenge is, as I mentioned a little bit of it right away, is that as we make things smaller, we still have to interact with them. So, we still have to put our hands on them. We still have to put our hands inside them. So you see a little bit of that reflected, let's say, in the design of that column oven and the column in the Lucidity system that we saw, where at least in the first time around with the system, and again, maybe Alicia, you can fill us in on this one as well. It made, it sort of limited what you could do with the column because you had the smaller oven. And where with the larger oven, there are all kinds of things you can do with the column holder and things like that. So that's one of, it does then become one of the challenges, is that small column oven. We really can't stick our hands in there to do stuff with it. So that then impacts how you're going to attach the columns. As one example. So that, I think, is one of the challenges. We see other GCs, and you'll see actually a lot of in the scientific literature, a lot of stuff about labs on a chip and things like that. But we still have to inject samples into them and do that reproducibly, and do that without think about what we're going to do when it's time to trim the column and things like that. So those are, I think, are some of the some of the engineering challenges that obviously vendors are also starting to overcome.
All
Yeah,
right,
I can
thank you.
add a little bit. Sorry, Leanne, I keep
Go
on.
ahead,
Nope,
please.
it's quite all right. I should give you the space.
No, but I think it's some great discussion here. But yeah, just like Tom said, it is a challenge. And he did put that one picture in his presentation that was a fairly older column holder. So an updated one does have standard fittings and ferrules. And if anything, it might actually be a little bit easier than putting it in directly into the oven, because you're installing it on the column holder itself, right there on the bench top. But the same fittings and ferrules, and you can trim it the same way you would normally trim a column. So that's kind of how we're getting over that. There is that limitation in the fact that it has to be wound at a specific diameter, which is 4 inches or less there. But most standard columns can get wound at that particular diameter.
Thank you.
All right,
Awesome.
thank you. So, what is your opinion on whether greening a method is optimization or compromise?
Thank you. That's a, yeah, that's a, that's a rough one. My opinion today is, and I'm going to really hedge on this because I kind of, as I started off with, it may end up being method specific as we really get into doing that optimization for greenness, as well as productivity and as well as things like sensitivity. Usually we think about sensitivity and productivity, and now we're adding greenness to that. I want to hedge a little bit, and I think we're going to probably see a little bit of both. I think some methods will green up very nicely, and other methods maybe not so much. I might use a little bit of an example from my work in SPME, which has been over the years has really been toward the analysis of drugs. And drug analytical chemistry methods are usually fairly complex because we're extracting the drugs from urine or blood or some other nasty thing like that. And so what would happen is, the SPME method might be greener, but the urine gums up the fibers a lot faster than extracting from water, and the fibers are more expensive. So all of those factors come into play. I think one of the things to think about, I think at the end of the day, we're going to find, probably like almost every other process, when companies think about sustainability and designing sustainability into things like manufacturing, I think we're going to see a pretty similar impact on analytical methods at the end of the day, but we're probably going to make some compromises to get there. That ultimately the green methods will end up being just as sensitive, but also more efficient than traditional methods when we get there. But there's a long way to go, and that's why, again, I showed you the issue number one of a green chemistry journal, or green analytical chemistry journal. We're really just at the kind of at the beginning of a journey of greening analytical chemistry.
All right, Alicia, do you have anything to add?
No, I think Nick knows more about that area than I do.
Very well. All right, then our next question, sticking with our green theme, what would you say makes microwave assisted extraction greener than traditional solid phase extraction?
Thank you. That's also a great question. And I'm thinking about microwave assisted extraction as a green technique, really because at first I see the microwave as, it's a smaller cavity than, let's say, things like your microwave oven at home and things like that. So it's there is some power utilization in there, but it's relatively low. But what I think about that is the ability to use the microwaves in all kinds of different contexts to perhaps open up a larger variety of solvents that I can use. And I'm starting to think about it, can I get away from using some of the nastier solvents like dichloromethane and things like that? If I can do a microwave assisted extraction into water or into a much more environmentally friendly solvent, and then work from there, that might be a little bit better than doing solid phase extraction, where of course in solid phase extraction, I'm still using solvent, and you know, 5 and 10 milliliters at a sample. And then when I think about it, where does a lot of that solvent end up going? Yeah, I think there's some, again, I think there's some possibility there. Um, but and those are the kinds of things that also may be method specific when we really start thinking about the volumes. One of the things I've been especially interested in is, can we reduce the volume of solvents that we use? And certainly there are ways to do that with solid phase extraction. SPME was really originally envisioned as a way to do that, but can can we take advantage of, let's say, faster kinetics to reduce and to help us in, let's say, reducing the volume of solvent that we might need for an extraction? I think so. There just gives us, the microwave extraction, I think, gives us a lot of interesting choices that we can use with solvents. And I go back to that one slide I showed with the theoretical development. And one of the things that we're looking at actually is just keeping it really simple and extracting into water. And then asking the question, how well does the GC column stand up to the water injections? And actually it'll probably stand up better than they used to. So those are the kinds of things that we're thinking about. And also at the same time, breaking some of those classical assumptions like you can't inject water in gas chromatography. Well, actually you can. You'll have to do some extra work to do it, but it can be done. So I think there's some good possibility for MAE to add even more to it through our, as a tool than we've traditionally used it so far.
Gotcha. No, that's fascinating. I did not know you could inject water on a GC column. So I'm even learning things today.
Well, you can't. You can. You got to be a little careful, and the vendors don't want to. A lot of the column vendors really don't want to. Kind of don't want to admit it, but you can.
Good to know.
Give it a try.
All
Again,
right.
be a good scientist. Try it and see, and you'll have to see how it works for you in your own context, or not.
All right. Well, continuing on, what industries do you see a lot of greening happening, and where are some that could use more optimization?
Oh, that's a good. Well, I think right now in terms of, I'm gonna stick to analytical chemistry, which is at least the topic that I know, and I think you know, I think, and you know, one way or another, I think everybody's going to be on what we're going to call the green. If I want to call it, be simplistic and call it a green chemistry bandwagon, I think everybody has to look at sustainability today in their processes. So I'm not going to call out particular industries or not call them out, because I think just about everybody is at least starting to think about sustainability and what they do going forward. Because one of the things you realize very quickly is thinking about sustainability is also thinking about saving money. And I think one of the, we didn't touch on it quite as much today, but one of the things that we've been thinking about, and I mentioned it a few times, is just thinking about your analytical methods. When you develop an ideal gas chromatographic method, one of the things that I would teach you in a course is have as little baseline as possible. Well, as little baseline as possible, that means I'm always looking at peaks. that means that I'm making my method as efficient as possible. And, just doing the things that we all want to do, like taking a 60-minute run and making it into a 30-minute run. You can think of that as greening the method, because if nothing else, if I run the same number of samples, I'm doing 50% less effort on that, or 50% less running the instrument. That means I can maybe get 2 instruments worth of work out of 1 instrument now, which is also a way of greening things. So that's what I'm really thinking about here, is how do we really think about sustainability instead of just throwing more hardware at it as we get more problems.
Gotcha. So this is more of a, I guess, your application question, but when you change carrier gases, is the offset standard from gas to gas or independent of sample, or is it sample and gas specific?
That's a great question, and I think that's again, what you're going to typically see, and we saw a little bit of that data today, is you'll probably see the whole chromatogram. If you do what I suggested and just take the new carrier gas, and it's not a bad place to start. Run whatever conditions you already have. Just switch one variable at a time. So change, let's say, from helium to nitrogen, which is which were the slides that I showed. Yeah, we saw a shift towards slightly slower retention times across the board because the nitrogen is slightly less viscous than the helium. And that meant it flows through faster. And hydrogen is less viscous than both of them. So it right off the bat, we'll see a shift to shorter retention times. Now, that may also cause you to lose some separation. So then you might then have to back that off with the temperature. But as a first step, when you see it in that first step, going from helium to either nitrogen or hydrogen, you're most likely to see all of your retention time shifted toward shorter.
Right. And it looks like we have our very last question. If someone wanted to make just one step towards greening their chromatography, what would you recommend?
That's a great question. If I wanted to look at one thing, I think I would go back to what I suggested a few moments ago and try optimizing for speed. And think about how you can reduce the time that you're looking at baseline instead of looking at peaks. A good thing to try is if you're running your traditional GC or even running a mini GC, um, take your take your temperature program that you're doing and double the programming rate, and you'll probably be pleasantly surprised. So think about, I think about a good way to start is just do the traditional optimization that you might do anyway, but think about optimizing for speed, because that way you get more samples done in a shorter amount of time. And you're either running the instrument less, or you're getting more samples done on one instrument. You're getting more work done really with the same amount of power consumption and other things that you have to do to support the instrument. So that's probably a good one good place to start right away that everybody can think about.
Excellent advice. Dr. Snow, thank you so much for joining us. And Alicia, thank you so much for joining us today. This now concludes our presentation. We hope that everyone will join us again next Wednesday for Dr. James Grinius's presentation, as well as Dr. Manuela Gianfrido's presentation.
Yes,
We thank you for your thank
I'm
you
just
for
going
your
to interrupt
time
and
today.
say, do join for those two. Those two are both rocket scientists for this stuff.
Excellent. We're ending on a high note then. Thank you guys so much and have a great day.
Thank you.